For long, humans have gazed at the sky, dreaming of flight, a realm once considered exclusive to the gods. This dream has been etched in our souls, passed down through generations, igniting our imaginations and fueling our ambitions. Our fascination with flight has pushed us to create myths of winged creatures and gods that soar through the heavens, captivating our minds and spirits. Our relentless pursuit of this dream came to fruition in 1903 when the Wright brothers took flight from Kitty Hawk, forever changing the course of human history. Since that momentous day, we have soared higher and faster, continually pushing the boundaries of what's possible. Our flights of fancy have transformed into tangible realities, from the thunderous roars of warplanes to the gentle hum of commercial jets, whisking us away to far-flung destinations. This is the journey we've embarked on, a journey that has seen us break the sound barrier and go beyond. If you've ever wondered how anything flies, let's break it down. First, let's talk about the forces at play. When an object takes to the air, something has to balance its weight, right? That's what we call lift. Lift is created by the pressure difference between the lower and upper surfaces of the object. But it's not all smooth sailing. The flying object also faces resistance from the air it moves through. This resistance is what we call drag. So to soar into the sky, an object must generate enough lift to overcome the drag force. It's a bit like a seesaw. On one side you've got lift, pushing up. On the other side you've got drag, pulling back. To fly smoothly, you need the right balance. This balance is often expressed as the lift-to-drag ratio. A good aircraft should generate a substantial amount of lift for every unit of drag. The higher the lift-to-drag ratio, the more efficient the flight. Now this all sounds pretty straightforward, right? But here's where things get a bit turbulent. Literally. Air is chaotic and behaves in a tumultuous manner. This is what we call turbulence. If you've heard of the butterfly effect, where a butterfly fluttering its wings in Brazil can cause a storm in Japan, it's the same idea. Airflow is unpredictable and ever-changing. This turbulence throws a wrench into the works. It makes the task of flying an aircraft, or even a tiny butterfly, more complicated than you might think. The complexity of air dynamics, particularly turbulence, makes modeling airflow a challenging task. But understanding these complexities is crucial. It's what allows us to design more efficient aircraft and achieve amazing speeds. So the next time you see a bird soaring through the sky or a plane jetting off into the clouds, remember the science that's at play. The lift, the drag, the turbulence. It's all part of the fascinating science of flight. The key to faster and more efficient flight lies in our ability to model airflow around objects. Imagine a river flowing smoothly around rocks, creating eddies and whirlpools. Now, think of that river as air, and the rocks as an aircraft or a bird in flight. This is essentially what we're trying to model when we talk about airflow. We're trying to predict how air, a fluid substance, will behave when it encounters an object. To do this, we use a branch of fluid dynamics called computational fluid dynamics, or CFD for short. CFD uses mathematical equations and numerical methods to simulate and analyze the flow of air around objects. It's like having a superpowered crystal ball that can predict how air will behave in various scenarios. However, as you might imagine, this is no easy feat. Air, like any fluid, is chaotic and unpredictable. It can swirl, twist and turn in unexpected ways. This phenomenon, known as turbulence, is one of the biggest challenges in modeling airflow. It's like trying to predict the exact path of a leaf in a storm. Moreover, running these simulations can be both costly and time-consuming. It's not just about the money spent on powerful computers and software, but also the hours, days, or even weeks spent waiting for results. For increasingly complex designs, such as a new type of aircraft or a high-performance sports car, the costs and time required can skyrocket. Despite these challenges, the importance of understanding and predicting airflow cannot be overstated. It's the key to creating more efficient and faster aircraft, cars, and even buildings. And as we push the boundaries of design and technology, the need for more advanced tools to model airflow becomes evident. Enter quantum computing. Promising to revolutionize many areas of science and technology, quantum computing could be the game changer in our quest to model airflow. With its ability to process complex calculations at lightning speed, it offers a hopeful glimpse into the future of fluid dynamics. As we strive for better designs, the need for more advanced tools becomes evident. Enter quantum computing. Quantum computing, a burgeoning field, promises a revolutionary approach to solving our airflow modeling challenges. Imagine a computer so powerful that it can process complex calculations in a fraction of the time traditional computers would take. That's the promise of quantum computing. It harnesses the peculiar laws of quantum mechanics to deliver a huge leap forward in computation. By applying quantum computing to the challenge of airflow modeling, we could significantly speed up the process of designing new aircraft, making them more efficient and even faster. Imagine planes that consume less fuel, emit less carbon, and whiz you to your destination in record time. Quantum computing could even help us better understand and predict turbulence, making flights smoother and safer. As we stand on the brink of a quantum revolution, we may soon see the dawn of a new era in flight, bringing us closer to the once elusive dream of effortlessly soaring through the skies.